Hello, everyone. I hope everybody's doing as good as I am, or better. Hopefully, better. I'm not doing that well. My eye got better. Kept soaking it all day long yesterday, and maybe it was just a little overkill, but you can't be too sure with when you have cement in your eye. Anyways, what did we discuss yesterday? We were discussing the neutron. And today I think we're going to continue a little bit with it, dealing with the neutron. And the first thing I want to say is please let me know if there's a problem with the sound. We've had all kinds of headaches with the sound in the last 2, maybe 3 weeks. And I corrected something. Apparently, I had two microphones running, and I'm going to test that today, essentially, because what I don't understand, even if I had two microphones running at the same time, I don't understand why the problem came in 50 minutes into, the lecture. And so that is completely baffling to me. But we're trying to figure out what the problems with sounds are. We've corrected some things these last 2 weeks, and hopefully we'll once we zero in on the problem, we can figure out what to take care of. If you have any ideas, please be feel comfortable to send some notes and saying what we can do to solve the problem. Hopefully. We don't have a problem today. Anyways, we did the neutron, and before I get into that, I'd like to one more time remind everyone we have the sixth rational physics conference in Buenos Aires, Argentina, and I'm going to put our what is it our propaganda our I guess the icon or whatever for the conference in Buenos Aires. There, it's going to be on the 10th of let me get a little to the side. 10th of November, Saturday. Probably going to be at 10 o'clock. I've got it there. What is it? I've got it too small there to see it myself. Yeah, it says 9 a.m. It's probably going to be at 10 a.m. And I'm going to feel sorry for anyone who doesn't come. We're going to have a lot of fun, believe me. And all you can do is look at the presentations after they're done, okay? And we have a little offer from Martin. Maybe it was tongue in cheek. I don't want to put him on the spot. But he says that maybe next year we can have it in Borås. I hope I pronounced that properly. Borås, Sweden. And this is where Borås is. I got a little picture of it. Okay, so that's where it's at, near a lake. You can look up the city in Sweden, and that's what the town looks like there on the right. And maybe we might have it in Sweden. If we can arrange it there, that's fine. So everyone again is invited to come to that conference if we decide to have it there. And again, I don't want to put Martin on the spot. Maybe he might disagree. Hey, I was just joking. Okay, fine. No problem. In that case, we might have it here in Frankfurt. So just keep that in mind. Anyways, we were talking about the neutron, and let me start at the beginning. And I'm just going to do a little quick recap. I start with the golden principle of physics. Physics requires an object. You can't do physics without an object, okay? And an object is that which has shape. That's our starting point in physics. And really that should, what can I say? I would propose that every presentation, every conference, people should start with those two things, making sure, it's like an oath that you swear before testifying in court. This would be like an oath you swear to before giving your presentation, your dissertation. We can't do physics without objects, and someone who says that we can is not a physicist. What can I say? He's an irrational individual. Okay, Martin says the following. He says, already started planning, but I will not go public until the 6th is over. Yeah, okay, no problem, Martin. So if you're serious about it, we'll keep in touch and we'll try to organize it there in Boris. Okay, and thank you for the invitation. We're gonna do our best to, if we decide to do it there, we can get it going. We'll organize it there. Okay, and thanks for the offer. Anyways, so we start with the this golden principle, as I call it. It's an inviolable principle. It's non-negotiable. We must have an object in physics. Otherwise, what are you doing? You're moving concepts around. What sense does that make? Does Mother Nature understand what a concept is? Can you move a concept around? The answer, in my humble opinion, is no. And so anyone who says that they're going to be doing physics by moving concepts, and I've got lots of those people out there, they're not physicists. They're mathematicians or amateurs, people who have no idea what physics is about. So we have to have the golden principle. We can only move objects, okay? So we have to have an object, and you have to define the word object if that's the bread and butter, the, what is it, the building block of physics. You have to define the term object. You have to know what an object is. And we define it as that which has shape. Okay? So that's our starting point. Okay? So we're going to the neutron. Hopefully the neutron is a physical object. We're not going to say that the neutron is a concept. And let me give you an example just so you know what I'm talking about. I can't say that the neutron is a field. A field? What is a field? How can you say that the neutron is a field, that a particle is a field? And when you look up the word field, one notion is that this thing extends all the way. It's like, think of it, a three-dimensional spider's web that extends all the way to the edge of the universe. That's the notion mathematicians have of the word field. How is it defined? The word field is defined as a value at each point in space around some kind of object. It could be an electrical field, it could be a magnetic field, it could be a muonic field, a pionic field. For every particle, there's a field. There's this bundle of bees around the beehive, and all these bees extend to the edge of the universe, getting lighter and lighter or thinner or less denser as you get out. That's the notion of a field. And to say that the neutron, the electron, the atom, the proton, that everything subatomic is a field is just eluding the question. You're not answering, you're not identifying the object. You're just eluding the question. So the word field cannot be used. And to add two more testimonies to that, I always like to use them. The first one is Faraday's, and the second one is Maxwell's. Faraday studied especially magnetic field, but he's also studied electric fields for many years. He was one of the first guys that really dedicated his time to studying these things. What he did was he ran a lot of experiments in his lab, and he inherited the lab from Davy, who had died earlier, and just he just kind of inherited the job. And he worked on it for many years. And so Faraday had a good idea after observing it for so many years. Not a sophisticated stuff that we have today, but he did play with a little magnet. He studied it to exhaustion. So he could tell you something about that little magnet, and you can say that forms the foundations of what a magnet is. So you can't blame the guy. He wasn't a stupid idiot. He knew something about it. He did dedicate his time. He tried to figure it out. So what did he come up with? He says, look, I'll call it lines of force. He didn't say it in these words. I'm putting words in his mouth, but he referred to it as lines of force, but he says, look, there's something physical in there. I just can't put my finger on it. I'll just call it a field because I have no other way of relating to it. So he said, look, I'm going to call it a field, and I'm just going to tell you what I observed in the lab, but there is something there, and it's physical. That comes from the horse's mouth, okay? And the other guy, Maxwell, he said, there is matter in motion. Matter in motion. That's what a field is. Matter in motion. And he was referring primarily to a magnetic field, but it could be the electromagnetic field, okay? Light, magnetism, electricity. He says, we call them fields, but there's matter in motion. That's the component. He couldn't identify it either. He described it mathematically, but he couldn't draw it for you. Okay? So field is a wrong word to use in lieu of particle. Keep that in mind, because that's the word that now is being used by quantum mechanics to refer to particles. Oh, a particle? Well, it's not a corpuscle. It's not Newton's corpuscle. It's really a field. So what is a field? Well, a field, you got to go to the university to study what a field is. It's not a little baseball, in other words. That's what it is. Okay, so having said that, what is the neutron? I started the discussion or the debate or the war. I'll call it a war. Is that okay? Started the war.
Crusade.
My son just joined me. Okay. I started the war by pointing out to this. This is my atom. It's on the left-hand side. I'm going to make it bigger, just so, and I'll bring it back. Okay, but I'm going to make it bigger just so you can see it. See what we've got there. That's the atom, and again, we have a proton in the center. And that red circle that surrounds that's going to be the electron shell. In other words, the atom, this is a cross section. This is a two-dimensional picture of the atom. And I hope I'm still doing okay with the sound. Mm-hmm. I'm doing okay? Okay. I'm so worried about that, so I might interrupt every now and then to check my bearings, okay? But anyways, that's the atom. We have the proton in the center. What is the proton made of?
This is of a hydrogen atom, right?
This is the hydrogen. Yeah, we're going with the simplest atom, which is complex enough. I mean,
my dad showed me what was it? Calcium atom?
Calcium atom.
It's a monster.
Yeah, don't give away my presentation here. Anyway.
Oh, sorry.
They might say, why did he show you the calcium atom? Well, that's what I'm going to be presenting in Buenos Aires. So those who missed it, well, tough luck for you, okay? Anyways, this is the atom, the hydrogen atom. As you can see, it's got a little dot in the center. But if you look close enough, you'll see little lines coming out of there. It's a little sea urchin with all the quills extending outwards. What are those little lines? Those are threads, just single threads. Okay, they extend rectilinearly, or straight in this case. They extend straight into the atom out the other end. Okay, this is the model. You don't have to agree with it. I'm just showing you what the model that I'm going to that I deal with. And it's circled by that electron shell, that red circle. And from there on, you will see not threads but ropes. So you have the ropes from every atom in the universe end at the electron shell. What continues after the two threads fork out is a single thread that goes to the proton and another thread that goes around and forms the electron shell. That's the atom.
A nice way to look at this is kind of color-coded, where the center is blue, the outside is the circle is red, and everything past that is purple. Both of them put together. I mean, that's not how it actually is.
It is. It is. The issue is that we can't see. It looks maybe kind of reddish, but it is.
It's a good way to color code it in your head.
Yeah.
Blue center.
Let's see if we can make it. If I can make it bigger, we can see the ropes there. Let's see. There it is.
The gist is basically every rope coming out of the outer circle.
Yeah, there you can see the ropes a little better. You can see that they are ropes.
Yeah, but you got a ring, and all the lines coming out of the ring are made of the shell and the center.
Yeah, here you can see it. You can see a little better, hopefully. You see the rope coming into and ending at the electron shell. What continues is the blue thread, just a single thread. The red thread, it goes around and forms the electron shell. And this we owe this image really to Mr. Dave Robinson. He's done a great job in putting this up there, and I have stolen it from him. I give him all the credit.
But you can't draw it.
No, I wouldn't have done such a good job as he did.
Because you need Photoshop for this, not paint.
Anyways, you guys should thank him, because this is a good image, at least of what I'm referring to. You may not agree with this. You may have a different version. That's fine. Okay, that's the atom. Let's now go a little deeper because what we're trying to get to here is to the neutron. And the neutron is next door to it here. Well, let's see, I'll just move it sideways here. Here's the neutron. Let's see if we can fit it all in there. Make it a little smaller maybe so that I can talk intelligently about it. Okay, here it is. If every atom in the universe is connected to every other atom in the universe, via an electromagnetic rope, a twined piece of pair of threads. At some point, all these ropes have to meet. They have to crisscross somewhere in the universe. In fact, they should crisscross just about everywhere in the universe. And I'm saying that everywhere is what forms the background radiation. What is it? I forget the word. Not microscope. Copy. What is the macro? Okay, I forgot the word. The background radiation. I think most of you know what I'm talking about.
What is it in a nutshell?
Well, what they've noticed, this was noticed by Penzias and Wilson I think it was 1963. They were looking at the sky. They got the Nobel Prize for this, by the way, and they were pointing their equipment at the sky for, I don't know if it was General Electric, some big company, and they were pointing their dishes at the sky, and they sensed like a radiation, a constant radiation, which was measured to be around 3 degrees Kelvin, okay, almost 0 degrees, absolute zero, very close to that. And they saw this background radiation. They couldn't figure it out what it was. And so they just stumbled on it by sheer coincidence, kind of. And they got the Nobel Prize for just, for discovering it. And then other people said, oh, you know what you've discovered? You've discovered a microwave. That's what I want to say. The microwave background radiation, which was theorized a few years earlier. They said, oh, you guys hit it on the nose.
Everything was theorized at some point. Everything was theorized at some point.
Well, no, sometimes it's the other way around. You discover something and then you theorize about it. Here, it was theorized, or like they say, predicted. And Penzias and Wilson, they discovered this background radiation. They got the Nobel for picking up on it. And anyways, I'm saying all these neutrons, all these vibrations of ropes, of concentrations of ropes, of crisscrossing of ropes, of convergence of ropes, all that's what the neutron is.
I already don't like where this is going. I got way too many questions.
Okay, that's what we're here for. Anyways, on the left-hand side, you see it blow up of it, and that's the neutron. It's just a convergence of ropes versus, and here I've got a better picture of it, versus the proton. Here you have them side by side. The proton is just going to be a convergence of threads, and the neutron is going to be a convergence of ropes. The difference is that the atom has, on the left there, it does produce what is called charge. It produces something that we detect, that we can measure, that we can quantify, and that's going to be the pumping, the back and forth pumping of the electron shell. That's going to be the what we call charge. That's going to be the caused by the what is called quantum jump. In other words, the electron, according to Niels Bohr, okay, he came up with this in the first quarter of the 20th century. He said, look, what I can tell is the electron jumps back and forth from energy level to energy level, which later on became what are known as orbitals. So here's the electron. It falls from one orbital, which is on a higher energy level, falls to a lower orbital or lower energy level, and bounces back. It just goes back and forth, back and forth, back and forth, and that back and forth produces light, electromagnetic waves or signals or whatever you want to call them, photons, okay? And I'm saying what Niels Bohr discovered is that a balloon is inflating and deflating. It's expanding and contracting.
Oh, you gotta go slow here.
Okay. So we think of the balloon, the electron, as a balloon. What you're seeing here is a cross on the left-hand side, by the way. You're seeing that red circle is the electron balloon. Its cross-section is a two-dimensional version of it, and that electron shell contracts and expands constantly. And what Niels Bohr was able to do is pinpoint the location of a point of a location of a location on the electron shell, on the balloon. And that thing goes back and forth because it's pumping. And he said, look, when it's on a lower end, it releases energy. And when the balloon expands, it absorbs, the atom absorbs energy. And so what are we talking about? Well, we're saying that when the balloon contracts, it releases one link of rope. And when it expands, it swallows one link of rope. That's what it's doing. It's going back and forth. And that's what the atom is. It's just a little heart that pumps electromagnetic waves, torsions, three-dimensional torsions along the ropes to every atom in the universe. Every atom, hydrogen atom, does exactly the same thing. And let's stick with hydrogen atoms because it gets very complicated as soon as you get beyond that. Okay, so that's our model, okay? And now, of course, people who follow the rope model, they have different versions. They say, well, I've got a different idea, and that's what we're here for. We want to brainstorm as much as you can. And please don't be ashamed. Please don't feel that someone's going to beat you up. We're talking about an invisible entity. Anything is acceptable. Believe me, if you introduce spirits, I'll accept it too, okay?
For the time being.
For the time being, we're going to accept all ideas. We want to brainstorm. I want to get to the bottom of it. It's not like, I've got this, just settled and say, well, this is it and you got to take it. No, it's like I'm investigating. I'm trying to look to see what this really looks like in real life, out there. Maybe someone's got a better idea than me, and I want to hear to all the ideas. You want to introduce spirits? You want to introduce God? Go ahead and do it. I'm going to consider everything right now, okay? Okay, so this is my model, okay? And I did add one little bit there yesterday, and that's the conversion. We're going to talk about this today, where the neutron, a free neutron, converts into a hydrogen atom, and a hydrogen atom converts into a neutron every 15 minutes. And parallel to that, we have what we got there on the screen. That's when the atom absorbs a neutron, and that neutron, you can see the first picture there on the top left, that's just the atom, and the neutron, the little pink star there, it's outside of it. As soon as the atom expands, in other words, as soon as the electron shell expands, it absorbs that neutron, and now you have a proton and a neutron right there in the center, okay? And Dan, I think it was yesterday, he came up with a good idea, which I liked a lot, really quite a bit, and I'm considering it seriously, and that's that they could both superimpose upon themselves. I probably have the picture there. Here, let's see if I can put it because it's pertinent. Dan, where is Dan? I think it's this one here. And Dan came up with this one, where the if you look at A over no, it's better to look at C. He's got a better picture. I'll go with the first picture that I put up for yesterday. This is the better one here to explain this, and that's if you look at the picture number, which one is it? The last picture, the one on the bottom right. Okay, you can see that there is a thread and there's a rope. There's a thread, there's a rope, there's a thread and a rope all going around. Okay, inside the circle. And I think what he's showing here, which I like a lot, is that the proton and the neutron, they superimpose, they both have the same center. Okay? So, whereas I can put this one, deuterium here, whereas my version of it is that they're side by side. That's the second picture, the one on the right, on the top right, okay? You can see that the proton and the neutron are side by side. Whereas he shows in his picture, I'll put it right next to it, right there, okay? He shows that they superimpose, and I like that a lot. So that's good brain work by Dan there, okay? I give him credit for that.
in a way, we already have superposition, so that doesn't seem to be outside of Mother Nature's bag of tricks that we don't have.
Correct. And again, we look at that from the subatomic world, okay? So, Dan's version I like a lot. And, okay, well, it's for everyone to ponder. Anyways, what we have there is deuterium. Deuterium means that it's got a proton and a neutron. How do they determine that? Well, exactly, we can't say all the details that they work on in the lab, but what they're saying is they noticed that this hydrogen, this high isotope of hydrogen, has double the mass of a hydrogen atom. And the only way they explain is, well, it swallowed a neutron. So the regular hydrogen atom that's got a proton in the center and the electron on the outside somehow has twice the mass, and there's no element that's twice the mass, because keep in mind that helium, the next one down, it has 4, okay? So you can say that deuterium is like element number 2, which has, a proton and a neutron. And then the third one there, which you can see on the bottom right, there's another neutron, pink neutron in the vicinity, and the electron shell expands, the blue electron shell expands once more, and now it swallows that second neutron, which is the picture on the lower left. And so now you have 1 proton and 2 neutrons, and that's the supposedly the configuration of tritium.
And there they would all be superimposed as well.
Yeah, I would say they are possibly, but again, we have this other issue that let's assume they're not superimposed, which is my version, okay? And why is that? Why may that be important? It may be important because tritium is radioactive. Radioactivity means that it tends to get rid of a neutron. It tends to shoot it out, tends to expulse it. And what's the issue there? The issue, or the explanation for it under the Rope model, is that, when you have these 3 particles inside the electron shell, we're talking about tiny spaces there, right? And here you're like putting, baseballs, or let's look at a bigger ball. Let's say you're trying to put basketballs inside a balloon. Well, the first one is okay. The balloon can handle it. Now you put a second one, and so the balloon says, "Oh man, that's so tough to accept that one." And when you put a third one, and say, "Oh my God, you're really pushing your luck." So what does the balloon try to do? It wants to get rid of the basketballs that you're putting in there, and that's why it's radioactive. And I don't know if we can explain that under superposition. Okay, and that might be the only one criticism against the superposition model.
I kind of like your non-superimposed version because of what you said. If we have radioactivity and we explain it as such, that the electron shell can only hold so many of these particles, then it would be strange if they were all perfectly superimposed on each other and then one just flies off. It seems like it would need some sort of imbalance or some direction to shoot it at. I mean, at some point it's going to fly out anyway, so there is a point where it isn't superimposed.
Yeah,
start there.
And it could be, it could be that maybe they're just offset by a billionth of a billionth of a billionth, if we bring Carl Sagan here. Billionth of a billionth of a billionth of a
so they are in the
millimeter.
They are in the center, but not exactly on it.
Right. No. They could be. The center could be in the same place, but maybe the rays are slightly offset by, I don't know, a small amount.
But then their centers wouldn't be in the same place. Their centers would be off by a billionth of a millimeter or whatever.
And we can add something to that, and that is that, under the gluon model, these things juggle in there. So it could be that these things are not completely in the center or in the center at all times. They're just like, bouncing against each other in there,
One good question is
it could be like that.
I don't know how deep you want to go into this, because I got a lot of questions. But one
You're not the only one. Take a number.
Yeah. One quick question to that is how does the electron shell keep a supposed neutron, assuming a neutron looks like that?
Yeah.
How does the electron shell keep the neutron in?
Well, it just traps it. I mean, and again, we've got, maybe we can go with some of the questions that came up. One of them comes from Monkey. and he's got some ideas. Dan's got some ideas. Martin came up with ideas, and I want to cover those because maybe that'll address your question to see where all these fellows are coming from. You know, everybody's really
What have we brainstormed?
Yeah, we're brainstorming here still. You know, I think everybody is. So let's get rid of all this stuff for a second here. Let me get back in here. Okay, and so let's go with who's it? Where is he? Okay, here, let's go with a monkey here first. Okay, he says a neutron is said to decay into a proton. Okay, an electron and an antineutrino. Okay, well, we can forget about the antineutrino because I don't think these people have any idea what they're talking about. They don't know what a neutrino is. They say that a neutrino acts. What do they say? It interacts feebly with matter, whatever that means. So it's very hard to detect an antineutrino or a neutrino, and so that's just a bunch of math there. Okay, that's all it is. Essentially, a neutron decays into a proton and an electron. There's some residual, they say, and that's the antineutrino. If you are going to explain what they, referring to the mechanics, are saying, then you need to explain all of it. Good. I like that because you do have to cover every base. Of course, they have matter creation from the Big Bang on, so it is nothing for them to create newer and newer particles. Yeah, so fine, that's good criticism. Electrons cannot become protons, okay, because they are considered indivisible, but protons can become electrons. I have problems with that one. I don't know if the monk is being facetious, or otherwise he's going to have to explain that statement. I don't understand how a proton can become an electron. Okay, but it is the free neutron that converts to an electron, a proton and an antineutrino. Okay, so the free neutron. Okay, let's continue. I'm going to address that in 2 minutes here. Hopefully we'll have enough time to cover all the subject matter. So let's go with Monkey Mind's second criticism. He says, neutrons do not become hydrogen atoms, and hydrogen atoms do not become neutrons. Why doesn't an electron or a proton collapse? Of course, their answer is that the electron is a cloud. And a cloud means that the electron is everywhere at once, even for the hydrogen atom that only has one electron. So this one electron is everywhere at once, and it's at two places at once, and that's how they make the cloud. Okay, so it's not a discrete particle under the cloud model. But the Rope-Hypothesis answer is that the electron is a shell comprised of magnetic threads from every H atom in existence. So unless someone can explain to me why we need quantum Rope-Hypothesis, I'm sticking with H atoms incorporate neutrons, okay? Okay, and I think H atoms do incorporate neutrons as well. I think if I remember correctly from yesterday, the monk was saying that, an atom goes along the rope, encounters a neutron, and kind of swallows it, and it incorporates in it. I have a little bit of problem with that. I'm going to go into that if we have time to try to answer that question. Let's move on.
We've got enough questions.
Oh yeah, we have enough questions here for to last us a while. Here's Martin, and hopefully I don't confuse him with Tom today. He is trying to explain what is mating. Okay, we asked that question yesterday. It wasn't very clear.
What is mating?
Yeah, mating, like
Are
to
we in
mate.
the wrong class? That's biology.
Yeah, Martin was looking at the girl across the street, and she was so great. He was thinking about sex. He said, "Oh, mating." So, okay, fine. At the E shell, one rope splits, but the thread that should pass straight through would need to mate in order to form a new rope within the shell. Any rope within the E shell must come from mating, right, of two different atoms. Okay, that's not, the best thing, Martin, if you're still hearing me over there, would be to put this in pictures. I would love to see your idea in pictures. The best way is illustrated, and that way we can see, step by step, like if it takes 3-4 steps to do the mating, that probably would be the best way. So we can get a piece of your mind in here, and I would love to show what you have in your head here, okay? Okay, the rope length within equals the atom diameter. Okay, so we have a rope extends throughout the atomic diameter. We're talking about, again, the H atom. And he says the left behind thread has no way of mating with its original mate until that buddy has left his newly found gay thread, because he earlier had made a comment about, that it's two similar threads going together. The homos from two different atoms. Rope within the E shell, okay? So to keep its mental health, it spins around, 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 forming the shell. I propose that threads have to mate to maintain the shape of the atom. Okay, the best way, again, I think, is visualization. Picture's worth 1,000 words, Martin. And right now, we're trying to visualize this, and until I can put it in black and white, I don't want to put words in your mouth of what you're really referring to.
Yeah,
okay?
the devil's in the details here.
Yeah, it is. It is. There's but it's good. It's good to come up with different notions. This is good brainstorming. Okay, let's move on. I want to move on to Dan also. I want to cover everyone if I possibly can today. Let's go with Dan's model. And yesterday we saw his model. We saw it a minute ago here, and he says the following: under this neutron model, all that sort of thing is just detailed measurements of what the thread, ropes, and E-shells are doing. Yeah, and one of the things I said yesterday is that you don't want to put your hand in the fire for what they've uncovered or discovered in the lab. Okay? Keep in mind that they do something, but they interpret everything in terms of particles, which are not particles, they're fields. They're everywhere.
So it's kind of hard to even understand or sift through. Like, they'll say something,
Yeah.
the electron did something, and now you have to translate it into, okay, what could that really mean?
In terms of the rope.
Or is it even the electron in this case?
Yeah. So we have to be careful about interpretation, okay? And anyways, we all can do the best we can here, considering that we're relying on what they've observed or did not observe or indirectly interpreted.
Because we're not talking about their observation, we're
Right.
talking about their testimonial.
Right, correct.
That's the trick.
Correct, yeah. And the mathematical physicists have just converted these verbs into particles, correct. As far as bending of ropes is concerned, my ropes won't bend. Okay, you get a kudo for that. You get a beer for that if you go to Buenos Aires only. They would do anything rather than bend, ergo, switching ropes, okay? Yeah, okay, Martin. Martin says, you showed a picture of mating yesterday. Yeah, my rev on your chart.
You didn't get taken off of YouTube?
My rev on your chart, but I'll produce some more. Yeah, please do. Martin, if you're still hearing me, because I don't know if the sound is still good, okay, you may want to go one step at a time, very slowly, okay? Very slowly show us one picture at a time, how you show, this mating procedure. I would like to really pick your brain on this, okay?
So that we know exactly what the word mating is shorthand for.
Yeah, if I'm going to give you a bat over the head, I want to know what I did it for, okay?
Okay. You're going to get the bat either way.
Yeah, you're going to get the bat either way. Okay. So let's continue with that. Thread being a fundamental object can appear in the context of there being a single fundamental or multiple fundamental objects. I opt for the single, okay? If thread was a single fundamental entity, it would supersede relativity and maybe even existence itself. Okay, we're getting philosophical here. A single fundamental thread is never a lonely thread. Oh, okay. That's an interesting concept. I thought the poor guy was lonely, but
there was only one.
There was only one, but he says even though it's single, it's not lonely. Okay, can you relate to that? Yeah, you're single. Are you lonely?
Fine.
Okay, H atoms. H atoms are eternal objects that would always relate to each other. Thread, rope, and H atoms are in an eternal dance. Okay, good poetry there. H atom and neutron would ultimately be the same eternal object in a different form. Okay, that's essentially what I'm proposing. A single fundamental entity called thread makes up and connects all objects, so to deny this would mean we are not using the RH. Okay, right, I agree. And I think Monk agrees with that as well. Anyone who doesn't, well, just raise your hand, okay? I'll keep it in mind. The single fundamental object should always be a part of our reasoning along with eternal matter in motion. Okay, let me first address here the concerns that Monkey raised, which is an important point. And the point is that he says neutrons convert to atoms, atoms to neutrons, but neutrons that are free neutrons. Neutrons are just floating in space that are not within an atom. They're not trapped within an atom, okay? That's what we refer to as free neutrons. It turns out that beta decay, or so the mechanics tell us, keep that in mind, so the mechanics tell us, okay? This is their interpretation. They're saying it also occurs inside atoms. Neutrons converting to protons inside atoms, protons converting to neutrons inside atoms. Here's the picture. Okay, sorry, that's not the picture. Here's the, somewhere I have the picture. Where is it? Here's the picture. Let me show the picture first. That's beta decay, okay? Here's beta minus and beta plus decay. Beta minus, you have 6 protons, and you end up with 7 protons, and you have 8 neutrons, and that neutron loses a neutron, and that neutron converts to a proton. That's inside the atom. Okay, you can see the pluses and the red or orange neutrons there, and what happens is carbon-14 decays into nitrogen-14. It's a minus decay, beta decay, essentially neutron converted into a proton. And then the plus decay is the opposite. You have carbon-10 turns into boron-10, okay? We went from 6 protons to 5 protons, and from 4 neutrons to 5 neutrons, a proton converted into a neutron. Those are the things they claim happen inside the atom. Okay, and again, the best way I can explain it is that mechanism I showed you where you have the, and I should have put that up there, again I forgot, but essentially a neutron, the ropes that go all the way to the center of the neutron where all the ropes converge, one of the threads simply pulls out of there. And it doesn't break, it doesn't tear, okay? It just breaks out of there and forms the it forms the electron shell. Okay, so every rope releases one of it that's going to the center of where the neutron is it just comes out. It doesn't break because it's not tearing. What it does, it just comes out and becomes the electron shell. That's essentially it. And again, a picture's worth 1,000 words. I should have put that up there.
You need a movie for that. We're talking about behavior.
I do have the movie also for that in one of my videos. The Neutron 1 or Neutron 2, you can see that in there. Anyways, what's the explanation for this? Here I'm going to show you the explanation. That's this one here. Beta decay is one process that unstable atoms can use to become more stable. So we're talking about stability of atoms, okay? There are 2 types of beta decay, beta and minus and beta plus. During beta minus, a neutron in an atom's nucleus turns into a proton, okay? And that's in an atom's nucleus, it turns into a proton. So this is not a free neutron. It's one guy that's trapped in there, and he just decides to go from male to female or from female to male. He's a trans, okay? And an electron and an antineutrino, okay? And the electron and the antineutrino fly away from the nucleus, which now has one more proton than it started with, okay? So essentially, they just convert. And an atom of carbon with 6 protons becomes an atom of hydrogen with 7 protons. Okay, so that's essentially what this beta minus decay is. What is the beta plus? The opposite. A proton in an atom's nucleus turns into a neutron. Okay, this is the reaction then. Since an atom loses a proton during beta plus decay, it changes from one element to another. For example, after undergoing beta plus decay, an atom of carbon with 6 protons becomes an atom of boron with 5 protons. Okay, so keep in mind boron has 3 in its outer shell, okay, valence shell. But anyways, that's the situation. Essentially, what they're saying is that these elements or atoms, they have the ability to convert a neutron into a proton and proton into a neutron to become more stable. By doing so, they become a new element. Why is it a new element? Because when a proton becomes a neutron, it loses its charge. So now they can detect that and say, look, this guy weighs more but has the charge
Neutral.
of another guy.
Mhm.
And that's where, that they have to explain that, and they say, well, we'll call that beta decay, okay? And vice versa. The process is reversible. And so it not only happens in free neutrons, Monk, but it also happens to protons and neutrons inside atoms. And
Isn't the context of beta decay also important? Under what conditions it happens?
yeah, and again, we have to look at that as well. How do they produce this? Because I don't think, I'd have to look at this in more detail, but it sounds fishy to me that if you just, I work with boron for 15 years, and I've never seen a boron atom just sitting on the table, just waiting for it to say, okay, I'm going to turn into, a carbon atom, or the carbon atom into a boron atom. Or, I work with nitrogen, I work with carbon, and I'm, obviously there's something happening there. Are we talking about acceleration, smashing? Are we talking about the pressure inside the sun? I mean, I don't know under what condition. Is it higher temperature? Something triggers this to happen. Or is it that at least one proton inside every atom on Earth, in the world, in the universe
is by
and decides to do a transformation?
No, what I really mean is turn into a neutron, or from a neutron to a proton.
I mean, does it do all protons spontaneously convert together with one electron, convert into a neutron? Do all neutrons spontaneously every 15 minutes or so convert into a proton? Well, that's what they're suggesting here. Okay,
it seems very unstable.
Yeah, it looks, and again, I don't know what they mean about stability, because carbon-14 is quite stable. I mean, there is, you probably heard of carbon-14 dating, and it has a half-life and so on. It loses some material over time, and they can measure that, and they say, oh, this is how old this thing is, because it went from carbon-14 all the way to carbon-12, which is a standard one, right? Okay, so if carbon-14, which is unstable, converts it not into carbon-12, but into nitrogen, well, how does it do it? Does it do it just by expelling a neutron? Does it do it by converting the neutron into a proton?
You make it sound like the atom takes a shit or something.
Well, yeah, I mean, all we can do is go by what they have found in the lab, or what they, like An said here, what they testify. They're witnessing, okay? They're testifying, look, this is what we think happened here. We're going to call it beta decay, and from this element, it converted spontaneously. This unstable element converted to isotope, because it's usually the isotopes, okay? This unstable isotope converted into a different element that's just next to it on the periodic table. Typically, keep in mind, if you want to convert hydrogen to helium, you just don't wait and sit there and put 4 hydrogen atoms and say, well, let's see, I hope they convert into a helium.
I hope
it
they
doesn't
get
happen.
along.
Yeah, you got to compress them. You got to do something to them. And what these people are saying, look, you got a carbon-14 just sitting there. It's unstable. We know this because it's radioactive. And, it converts into the next element. Think about that. I mean, first think about what they're doing in the lab. Second thing, how you're going to explain that, assuming you concede that.
About the thing in the lab, a good way that I think of it is it's kind of like, and we're going to get to his comment.
Martin says, Principia of mating, okay? And your thread on atom versus neutron on RSM, bat away. Okay, we'll bat you away. Don't worry, Martin. If you want to have some lumps, you just tell me what side of the head you need it on, okay? Yeah.
You know what? What mathematical physics testifying is when they say what they observed, is kind of as if I went to an operating table and I had to tell you what I saw. I don't know all the details of what I'm seeing. I got to tell you, okay, I think this is what happened. I think this is what happened. So you kind of have to take my word for the interpretation. like I got to be like, okay, I think he cut his heart open, and then that's kind of what it is with physics when they're looking at something where they have to interpret whatever it is they're seeing. They can't just tell you exactly word by word
because they can't
frame
see
by
the
frame.
mediator. They
Yeah,
can only
yeah.
see the visible stuff, and they say, well, if we're going to do this with particles, this is our
They
explanation.
can only see the effects. That's the
Right.
problem. So they
And,
can't
and
really say.
they only see the effects of what is visible. And it's the invisible mediator that they're either skipping or missing or misinterpreting or whatever, right?
You got to kind of take it like the detective that kind of takes witnesses' testimonies
Right.
with a grain of salt.
Right. That's why you got to separate fact from interpretation of the fact. Okay. Anyways, what I was saying is the reaction or the conversion happens inside and outside. I thought it would only happen to free neutrons. No, it also happens inside neutrons that are inside atoms. They do convert into protons or protons into neutrons according to the official version. Okay. So again, we're trying to interpret in terms of the rope hypothesis what these people say they saw or experienced in the lab. And all we can do is rely on their testimony and say, okay, let's assume that what they are interpreting in terms of particles is correct. Let's concede that. Let's grant that. How do we explain it under rope model? Is it possible? Is it impossible? Okay, that's the situation. That's what we have to address.
Did you have something else to say about the beta decay? Because I had a question about neutron.
I have one more, I think, here. Let me just finish here. Here's the free neutron, by the way. I'm going to put that up there as well. Here's the free neutron decay. It says outside the nucleus, free neutrons are unstable and have a mean lifetime of blah, blah, blah. They put a whole bunch of numbers. 14 minutes, 42 seconds. 15 minutes, period, okay? That's the reaction. Neutron plus proton gives you, neutron turns into proton plus electron. Plus, as you always know, you have these neutrinos, antineutrinos on the outside that they don't know what they are. They interact poorly with matter, et cetera, et cetera. They don't know what they're talking about there. But essentially, it's a proton and an electron. And are they talking about two particles? No, they're saying, look, these are mathematical quantities. And we know that the neutron weighs approximately or has as much mass as a proton and an electron plus an almost massless neutrino.
Is the correct way of looking at this equation something like this interaction or effect? This effect plus this effect. If these two effects are in the same place, you get the neutron effect?
The way they're looking at
Something
this,
like
let's keep this clearly in mind. They're only looking at mass, possibly charge as well, but primarily mass. They're saying, look, a neutron weighs almost as much as a proton plus an electron, but there's a little residue there, and that residue is that antineutrino or neutrino there, whichever one, depending on which direction you go, whether you go from proton to neutron or atom to neutron, neutron to atom, okay? So in one case it's the neutrino, and the other one it's an antineutrino. But the point here, they're looking at mass. Keep that in mind. They're only looking at mass. And they're saying, look, if you have 10 kilograms here, and it disassociates itself into 9 kilograms of one thing and 1 kilogram of something else, and the 9 kilograms is the proton, the 1 kilogram is the electron. Okay, so we have 9 kilograms of proton plus 1 kilogram of electron gives you 10 kilograms of neutron. That's essentially what they're saying. They're doing it all with mass. Okay, they're weighing. How do they weigh these things? This is the way they weigh it. They supposedly accelerate the particles, which they think are particles. They're accelerating them along the beamline. They say, how much energy do we need to accelerate this monster? And they look at the energy in terms I work with kilo electron volts. These people work with giga electron volts, billions of electron volts. So it's you can say a high energy impulse. They're really pushing this thing quite fast, and they can measure that in the giga electron volts. And they say, look, if a neutron requires so many giga electron volts and a proton requires a little less, then we see what's happening. The neutron it has a little more mass than the proton, And still, if we add the proton and the electron, it doesn't match the neutron. So there's a little residue. What are we going to call that? Well, we'll call it the anti-neutrino. That's how they determine this. It's all math. Words that they apply to mathematical concepts. Okay, that's how they do this. Anyways, it involves the emission of a W boson. That's the W. That's the weak force. Keep in mind that's the weak force. Okay, that's what the W stands for. And W boson from one of the down quarks within the neutron, thereby converting the down quark into an up quark. Remember, the neutron has a down quark, and the proton has an up quark. That's essentially the difference between them. We have 3 quarks in each, and one of them in the neutron is a down quark, and the proton, that same quark, is a down quark. Okay, it's an up quark. I'm sorry. So that's the way it is. Okay. So the W then decays into the electron and the antineutrino. Okay, so that's the free neutron decay that happens outside. Neutrons that are free out there in middle of space, they don't belong to any atom. And here's the last one that I've got today. For the free, which is the explanation essentially, for the free neutron, the decay energy for this process, based on the rest masses. Keep in mind, rest masses of the neutron, proton, electron is, and that's that mega electron volts. Okay, again, that's the energy they need to accelerate these things. That's how they determine these things. That is the difference between the rest mass of the neutron and the sum of the rest masses of the products of electron and proton. That difference has to be carried away as kinetic energy. That's what the little guy, the antineutrino, is. It just flies off, and that's the kinetic energy they lost there. The maximal energy of the beta decay electron in the process wherein the neutrino received a vanishingly small amount of kinetic energy has been measured at blah, blah, blah. Okay, the latter number is not well enough measured to determine the comparatively tiny rest mass of the neutrino, which must in theory be subtracted from the maximal kinetic energy. Furthermore, neutrino mass is constrained by many other methods. Okay, so in the final there, small fraction, about 1 in 1,000 of free neutrons decay with the same products, but add an extra particle in the form of an emitted gamma ray. So when they can't explain it with a neutrino, they just add a fudge factor known as a gamma ray, and they fix the equation. It's all equations. We're not even talking about particles. You say, well, what are those things? Oh, they're all equations. They're all constants and variables. That's it. And they give a value to each one. They say, well, it still doesn't match. Okay, put a fudge factor. We'll call it a gamma ray, whatever. So that's how they determine these things. And all we can do is say, let's assume the math is correct. Let's concede that. Let's say if you take, an apple pie plus an orange pie, you get this other pie that weighs approximately the same as these other 2 pies. That's about as much as you can do. And now, how do we interpret that? Assuming we concede that, how do we determine that in terms of the rope hypothesis? That's our task. That's our job. That's where we have to brainstorm. Okay? So that's the situation today. That's about it. I just want to present the case so it gets you to think and see what you can come up with. My version, I'm going to see if I can bring the neutron conversion tomorrow if I don't forget. And I'm going to put that up there. I want you to see a little video of that if you haven't seen it already, okay? And the only thing I can do is present my case of what I think they're finding out in the lab. If you have a better version, hey, be my guest. We're again trying to brainstorm here, and we're trying to brainstorm an invisible entity. If you keep that in mind, no one can laugh at you. All you can do is brainstorm and see what you can come up with. With that, we'll see you tomorrow, same time, same station, and hopefully you'll be there. Bye-bye.